Okay, welcome everyone to the latest in our series of INQA seminars. This will be the last one before the summer break. And it gives me great pleasure to introduce Yuval Baum from Q-CTRL, who I guess is in California right now.
Yes.
And Yuval will be talking to us about quantum optimization at the utility scale. Over to you, Yuval.
Yes, thank you, Paul, and thank you for inviting me. It's great to be the last speaker of this session. So I know that this seminar is typically more focused on annealers and quantum annealers, but today I'm going to talk mostly about gate-based quantum computers, although as you probably, maybe some of you saw this paper. For some reason, I cannot turn my slides. Let me see. Let me just reshare it again. Sorry for that. All right. All right, let's see that now. Okay, perfect. Now it works. So the paper that we published recently has the words quantum annealers in its title. But for most of my talk, I'm not going to talk about this comparison of gate-based versus quantum annealers. I'm mostly going to talk about what are the challenges with gate-based quantum computers and what did we do in order to overcome these challenges. And at the very end, when I'm show you results, I'll compare these results with some data points that we have from quantum annealers. So overall, I'm going to introduce this concept of quantum solver or an optimization workflow. I'll take you through the details of the implementation, and then I'll show you some examples of executing these optimization problems on real quantum computers. So first, what do I mean by an optimization workflow or quantum solver? So I'm assuming that many of the people here are experts, and typically when experts want to solve a problem on a quantum computer, you know how to do all the different steps. You know how to represent the problem in a quantum-friendly way. You know how to embed this problem for the specific device at hand. You know how to implement different error suppression or error mitigation tools. You know how to read the data correctly. But most people, especially outside of the quantum world, this is not something that they can rationalize, understand, or do. They want an experience that is much more similar to classical solvers that exist out there. You define your problem in some abstract way. For example, you define a cost function in some symbolic way, like the one that I wrote here. It doesn't have to be quadratic as the one that I wrote here. Maybe you can define your problem as a graph and some task on this graph. Maybe you can even use some standardized format that classical solvers use, like Cplets, Garobi, and other kinds of commercially available solvers that exist out there. And our goal is to build a very similar experience. So as a user, you just need to define your problem in some abstract way. Everything else is in some sense under the hood. I know that this is typically what scientists are interested in, and this is going to be the topic of my talk, everything that is under the hood. But for most users, this is just going to be under the hood. And then for the user, they'll just see the end solution. So big part of our work is not just to invent these tools and methods, but also to make sure that we can automate that, we can make that literally real time, and we can optimize that for the specific problem and for the specific device that the user want to use. So today I'll talk about the methods themselves, but definitely big part of what we are trying to do is to also lower the barrier for people to use quantum computers. I think whether it's quantum annealers or gate-based quantum computers, this is something that in our community, we have this interest to push more and more people to use these devices and to see what can you get by using these devices today, and hopefully what we'll be able to get a few years from now. So what do we have under the hood? We have an optimization pipeline. So this optimization pipeline starts from the problem definition. This is typically user-defined. Then what we need to do, we need to understand how to take this problem and encode it to the quantum computer. So that means what is the type of quantum algorithm that we want to use in order to solve it, and how to embed the specific user-defined problem. Then we need to compile it. We need to embedded to the specific device at hand, whether it's a quantum annealer or a quantum computer. We may replace the basic operations. So in the context of gate-based quantum computers, we may replace the definition of the gates at the pulse level in order to have more optimal operation. Then typically on quantum computers, unlike quantum annealers, the quantum circuits or the quantum algorithms that we eventually have, they have some free parameters, and these free parameters should be optimized. And typically it is done in a closed loop manner. So we run the algorithm on the quantum computer, we read the results, we use some classical optimizer to update the parameters of the quantum circuit, and we run it again. So hopefully after several iterations like that, we find the optimal parameters. And then we end with a quantum algorithm, a quantum circuit with fixed parameters. And ideally, this quantum circuit can be thought of as a very good sampler, in the sense that if we'll now sample solution from this quantum algorithm, with very, very high probability, we're going to sample very high quality solutions. And in particular, we want that with high probability, we'll sample the optimal solution. So that will be a good sampler. And finally, once we have the optimal circuit and the results, we also allow ourselves to do some sort of post-processing before we return the results to the user. So in the not very long time I have, I'll try to take you through some of these parts and give you an intuition why they are important and how can we overcome some of the challenges that exist there. So the first thing that I want to talk about, which is not very chronological, you notice that every time we send a circuit or an algorithm to the quantum computer, actually executing it on the quantum computer, we always add error suppression to it. And the question is, why do we need to do that? And what will happen if we'll just remove that? We'll just use exactly the same pipeline, but without error suppression whenever we're sending a circuit to the quantum computer. So in order to understand why that is needed, we need to remember some of the secrets. These are not really secrets of currently available gate-based quantum computers. I don't know how many of you had the chance to actually execute a small program on quantum computers, but they tend to be quite noisy. So here I give a very simple example. This is a very small algorithm. This is a 5-qubit Grover algorithm. So on the top, you can see an ideal simulation of this algorithm, which we can do because it's only 5 qubits. So you can use a perfect simulator. And what you consider is the ideal outcome. This is the distribution over the 32 possible bit strings that you can get for 5 qubits. And what you can see in the bottom panel is the execution of exactly the same algorithm on a real quantum computer. Now, we don't need to go too deep into these results, just immediately look at it. And you can see that the output from the quantum computer is pretty much random. There is literally no signal that connects the ideal result with the true result. Now, I would say this is a year-old data, and devices today are a bit better, but it just tells you that even if at 5 qubits you'll see some signal, as you'll go to 10 and 15 qubits, eventually you're going to see the same thing. You're going to see that the results that you are getting from the quantum computers are pretty much random and they don't have any signal. So as devices are getting better, our appetite are getting bigger as well. So we are trying to push for bigger algorithms and deeper algorithms. And because of noise, it's unavoidable. We'll always hit this point where the output from the quantum computers are just completely noisy. So one of the tools that we developed at Q-Control, even before this optimization pipeline, is an error suppression pipeline. This is a different pipeline from the one that I showed you before. In some sense, this is a pipeline within a pipeline. And this error suppression pipeline acts on any quantum circuit, not just in the context of optimization. The input is a general quantum circuit, and then we're doing a bunch of operations, starting from very aggressive compilation, from error-aware mapping of the different qubits according to the device properties. We are inserting highly optimized sequences, such as dynamical decoupling, to eliminate crosstalk between different qubits. We replace gates at the pulse level to have a better implementation of the different operations, and we allow ourselves also to do some post-processing to account for readout misclassification. And the idea is that this is all, again, completely automated, real-time for the user. If you are interested in reading more about this specific pipeline, we have this paper from 2023 that specify these specific parts. This pipeline is actually natively available on IBM devices. If you go to an IBM device, the Q-control pipeline is just something that you need to click and you can use it. So this pipeline is available to users to use. And when you are using this error suppression, this is what you see. So here in the last panel, we take the exact same algorithm, we run it exactly on the same device. So the middle panel and the last panel is exactly the same circuit executed back to back, just immediately one after another on the same quantum device. And what you can see is that the last panel is not identical to the first panel to the ideal results, but it's very clear that there is signal there. We pretty much retrieve the signal on the given device just by using smart and efficient error suppression mechanism. Now, this is, of course, for an arbitrary algorithm. I still need to show you that it actually matters for the problem of optimization. So for that, we did a nice experiment where we generated a 40-node, 3-regular graph. So for those of you who are not familiar, a regular graph is a graph where each node is connected to exactly the other nodes. So when we have 3 regular graphs, these are graphs where each node is connected to exactly 3 other nodes. And of course, there are many graphs like that. So we randomly generated a 40-node, 3-regular graph. And what we wanted to know is what is the MaxCut? Or we wanted to sample different solutions or different partitioning of this graph. And for each partitioning, asking what is the cut value of these graphs. For those of you who are not familiar, so a cut is defined as an edge that connects two nodes with different colors. So you can think about this problem as just coloring the nodes of the graphs with 2 colors. And whenever you have an edge between 2 different colors, you count it as a cut. And now you ask how different partitioning, how different coloring of the graphs, what cut values they give you. And in order to do this comparison, we fixed the quantum circuit that we are running. So there is no optimization here. We did some pre-optimization. We have a well-defined circuit. We don't do any processing on this circuit. We just run this circuit on the quantum computer. We sample results. We don't do any type of post-processing. And we just sample 10,000 solutions from the quantum computer, and we plot the distribution of finding the cut value. And what you can see in the middle panel, this is what happens when we take the circuit as is and execute it and sample 10,000 times using the default execution on the quantum computer. Just as a reference, in the third panel, we put a completely random sampler. There is no quantum computer involved in the last part. We literally sample 10,000 random bit strings, each one of size 40, and we just plot the distribution of the cut values that we are getting there. And what you can see is that when you look at the default execution and the random, they're pretty much indistinguishable, which means that when you run on the quantum computer, the output is not distinguishable from just using a random sampler. So if that's the scenario, you can just take our pipeline and just replace the quantum computer by a random sampler. It's much faster, it's much cheaper, although it's not likely to be a very good solution. Yet when we use exactly the same circuit, executed on exactly the same device, but then together with the error suppression pipeline, now you can see that this distribution is shifted to the right. You have much higher probability to sample higher quality cuts, cut value or cost value that corresponds to harder and harder solution. In particular, you can see that you have, in this case, for this graph, non-negligible chance to measure cut values at the mid-40s that otherwise are extremely rare to sample if you just sample randomly. So the overall conclusion is that having the error suppression there is not an option, it's a must. If you don't do that, every time you send a job to the quantum computer, the result is pretty much random. So you can just take this block and replace it by a random sampler. The next thing that I want to give you a bit more details about is the actual algorithm that we are using. So for those of you who are a bit familiar with binary optimization on gate-based quantum computers, a very popular algorithm is the QAOA algorithm. The QAOA algorithm is in some sense, somehow a version of adiabatic evolution. It's a trotterized version of adiabatic evolution. And because quantum computers are still very limited by the error rate, so typically the number of trotter steps is truncated at relatively early stage. And in order to compensate for that, each layer is accompanied by some optimization parameter that can be tuned. So the hope is that using these optimization parameters, we can compensate for the fact that we truncate the trotter expansion of the quantum evolution at a relatively shallow version. But the main problem with the QAOA algorithm is that shallow QAOA algorithms are not very effective. This is a plot from a paper published by the quantum group at JP Morgan Chase. And what they showed is that when they're trying to solve MaxCut problems on 3 regular graphs at relatively small scale, these are 24 to 32 nodes, these are not big MaxCuts, and they used perfect simulators. So there's no error here. They used a perfect simulator, noiseless simulator, in order to achieve very, very good solutions that are competitive and can find the true optimal solution. The number of steps in the QAOA, the number of blocks, typically denoted by the letter P, that they needed to add was typically double digit, was above 10, around 11 or so. And other people published that in different contexts, you need to go to about 16. And overall, if you really want to scale to hundreds of qubits, it is likely that the number of layers, number of trotter layers that you need in this QAOA algorithm is likely to be above 20. And one thing to remember is that each such layer of QAOA has many different operations, many different gates. And as these gates are not perfect, they have some error, each such layer of QAOA is extremely costly. And with near term and probably even not in the mid to far future, running large scale problems with 20 or over 20 layers of QAOA is a no-go. Quantum computers will not be able to handle that because the number of gates that you'll need in order to execute that is probably at the tens of thousands, and that's just a lot given the error rate of current gates. So what we wanted to understand is how can we, on one hand, keep the QAOA shallow, in the sense that we won't have to take as many layers as described here, but on the other hand, have enough richness to be able to reach any possible state in the Hilbert space in that case. And the way that we did it, we just added more optimization parameters to the problem. So for those of you who are familiar, typically the QAOA is described by these colorful blocks. Each one block of a orange and blue described a single block of a QAOA. If you want, this is a trotterized version of the adiabatic evolution. There is some mixing Hamiltonian, and there is the problem Hamiltonian that you interpolate between. And then these parameters, gammas and beta, are the optimization parameters. And typically, the initial state for the QAOA algorithm is the full superposition, is an equal superposition among all possible states. And in the language of RY rotation, it would just mean that all these thetas, all these angles at the very beginning are pi over 2. Right? And RY of pi over 2 generate an equal and real superposition between the state 0 and state 1 of this specific qubit. And when you do it on all qubits, you just have a full superposition real between all possible states. But the problem with that is that as long as we truncate this QAOA after 3 layers or so, using the general initial state is just not good enough. Because even if I give you the solution, even if I tell you the solution is something, some oracle gave us the solution, finding the gammas and betas that will give us with high probability this solution is almost impossible. And actually, for very big problems, probably there is no such choice of gammas and betas as long as we keep it shallow that will give us the solution with high quality. On the other hand, if I let you also control these initial parameters, now if I give you the solution, it's pretty much trivial to generate that. Just take all these gammas and beta to 0, so that's identity, and then these thetas can just be either 0 or pi, right? When we set it to 0, it means that that qubit will be at the 0 state. And when we set it to pi, that qubit will be 100% of the time at the 1 state. Now, of course, in reality, we don't really know what is the solution. So as we optimize the parameters of this circuit, if ideally we'll do infinite optimization steps, we expect that at the very end, all these betas and gammas will go to 0, and all these thetas will go to their extreme values, either 0 on pi, and we'll get 100% of the time the optimal solution. In reality, of course, we don't have infinite steps. So eventually, we have some combination of angles between 0 and pi, and the betas and gammas are non-zero. So using these ansatz, of course, we can achieve much better states and much better solution, even with a relatively shallow QAOA, but there is a price to that. We added many more parameters that we need to optimize. So we added n more parameters where at the scale of 120, 130 qubits, these are quite a lot of optimization parameters. And this is part of our optimization strategy. So we have some sophisticated optimization strategy to find these parameters. This is not something that I'm going to talk about today, but we have it in our paper. So if you are interested in the optimization parameters, in the optimization algorithms for the circuit parameters, you may find it there. So the last thing before I'll show you some results that I want to talk about is post-processing. So after we build these ansatz, we compile it to the device, we run the optimization loop using our error suppression tool in order to determine all these different parameters, all these thetas and betas and gammas. Eventually, we have an optimal circuit, and that's the circuit that we sample from and hopefully get the solution. So we allow ourselves to add some post-processing to the data that we are getting from this optimal circuit. And what is the reason for that? The reason is that as we go to larger and larger scale, no matter how good our error suppression is, there are some errors that are unavoidable. And these are typically, they come from T1 effect. So as you run the circuit, there is always a chance that you'll have some uncorrelated random bit flip, just something that exists there. There is some probability for that. Also, when you measure a qubit, there is always some probability for readout misclassification. It may be that the state is 1, but you accidentally read it as 0, or vice versa. The state is 0 and you accidentally read it as 1. These are small probability errors, but remember, if you need to read 130 qubits, the chance that at least one of them will be misclassified is not that negligible. So typically, these type of errors that we cannot get rid of using our error suppression appears as just uncorrelated bit flip. So you sample a bit string with 120 or 130 values, and it may be that 2 or 3 of these bits will just be flipped in a very uncorrelated way. And in many executions of quantum algorithms, that's not that crucial because we sample many, many shots or many, many samples, and we average over that. So the hope is that if we have some small number of uncorrelated bit flips, it won't affect the results dramatically. But in the context of optimization problems, these are quite catastrophic errors because we are looking for rare events, and these rare events are typically configurations that any small change to them is going to dramatically lower the performance. So if we think about a deregular graph and solving the MaxCut problem, typically the optimal solutions are such that almost any node is maximizing the number of cuts that it can have. So just flipping one node typically is going to lower your cut value, or if you want, increase your cost value by a factor of d, where d is the connectivity of the graph. For example, it can be 5 or 6 or 7. So even if you have 150 qubits and only 4 of them were just accidentally in a very uncorrelated way were flipped, if you are using, let's say, a 7 regular graph, that's it. You are already 28 in value below the MaxCut. So you're very far away from the solution, even though you just had 4 uncorrelated random bit flips just by reading the state from the device. So this sensitivity is quite hard for quantum computers right now. And the way to have some robustness to that is to add a very simple and very efficient post-processing procedure, where we just take the final bit string and we just do a greedy linear scan. So we just scan this bit string, and for each qubit, we ask whether flipping it is going to improve the cost value. If yes, we accept it. If no, we move forward. Now, of course, in this case, imagine that we truly generated the right bit string, but accidentally three of the bits across the 100 and something bits that we have were just randomly in a very uncorrelated way were flipped. This post-processing pass is likely to correct that. So of course, it's not 100% of the time, but it gives us some robustness to this type of errors that currently we cannot get rid of. And in general, it scales linearly, it's extremely fast, it's literally real time. So, and we can definitely show that this pass alone, of course, cannot find the solution. Otherwise, these will be very trivial problems to solve if such a simple greedy bit flip pass can find the solution. All right, so if you want to know more details about other parts that I didn't talk about, so please go to our paper, or if you want to know more about our error suppression, please go to the second paper that I showed you. But I think in the remaining time that I have, I want to show you some examples and results of what happens when we are using this pipeline on real quantum computers. In this case, these are IBM quantum computers. So first, let's define the rules. So the first set of problems that we are studying are MaxCut problems. So MaxCut problems, if you consider them on random graphs and you also allow weights between the nodes, they pretty much can represent any QAOA, any quadratic unconstrained optimization. So although I'll always refer to it as MaxCut, in some sense, you can think about this set of problems as a very generic QAOA problems. So some of the rules that we defined for this benchmark, the first is we're using generic graphs. Remember that if you are using a specific quantum computer or specific quantum annealer, typically there is some device topology under the hood, and you can always try to match the graph of interest to your device topology. But that's, of course, a very non-generic, a very non-generic problem. Typically, what we want to test it on completely generic graphs and to see whether the quantum computers can handle these graphs. So in particular here, we'll just randomly generate D regular graphs where, again, each node is connected to exactly D other nodes. And we change this D all the way from 3 to 7. The reason that we do that is because we know that already from D equal 3, solving MaxCut problems on regular graphs is in general a hard problem for classical solvers. Although at these scales, I would say that very good solvers like industrial solvers such as Gurobi and Simplex can still solve it quite easily. So these are still sparse problems, even 7 regular, when we go to 100 and something nodes is relatively sparse, but on the other hand, it has non-trivial connectivity, definitely much higher than what the quantum device can support. Some of the other rules that we define, the full optimization is done on the quantum computer. So there is no use in some prior information that we have on the problem, on the symmetries of the problem. Definitely any use of some quantum simulator is absolutely not allowed. And in terms of post-processing, the only thing that we allow is what I described before. These are methods that do not add quantum execution time, that pretty much run in real time, and that scales linearly. So we know that even if tomorrow we'll have a system with 3,000 qubits, at least the post-processing is not going to be a bottleneck. All right, so here you can see 2 results, and I'll show you many more. So first, how to read these plots. So here we have 2 different problems that we wanted to solve. So on the left, we have a 3 regular graph with 120 nodes. This is an unweighted one, which means that all the weights are pretty much 1 on the edges. And on the right, we have 4 regular graphs with 18 nodes and with weights. The weights are described by these different colors of the edges. And what you can see here are distributions, or if you want, histograms of 3 different methods. Each method, we sample 10,000 candidate solutions, and for each solution, we ask what is the cut value of this solution. So the purple one is the optimal circuit that we are getting using our sampler. The gray one, the light gray one that you see very far away from the other distributions, is just random sampling. So we just randomly sample 10,000 bit strings, and we just ask what is their cut value. And the dark gray is a local solver, a classical solver. So this is something that is a bit equivalent to simulated annealing, for example. So it's a good solver. It's a decent solver. It's not as good as like the best industrial solvers such as Gurobi and Simplex, but it's a decent solver. And the last thing that you can see here is the red line. The red line is the optimal solution, in this case, calculated by Simplex. So Simplex is a classical solver, so you already understand that I'm not going to claim here any quantum advantage. Commercial classical solvers like Simplex, Gurobi, and others can still solve these problems easily, and we treat their solution as the ground truth. So we still assume that these are the true solutions. And what you can immediately see here is few things. First of all, random sampling is not very competitive. We should not use it as a benchmark because you can see it's just not very good. It's very, very far from the solution. But remember that until not too long ago, every time people use quantum computers, gate-based, that's what they saw. So the conclusion was very natural. Quantum computers are not very good in solving these problems. What you can also see is that we consistently sample the true solution with non-negligible probability, and that in general, even though the classical solver in this case can almost in all cases find the right solution with some probability, but can find the optimal solution, overall our sampler can sample better than this classical solver. And we do it for a variety of problems. I'm not going to show you all of them. We do that with different random seeds of the graphs that we sample. We do it with different connectivity, with different nodes. And 100% of the time, for all the problems that we consider, we can always sample the optimal solution with relatively high probability. And in all cases, we outperform the classical local solver. Again, not all classical solvers, but the classical local solver. The last problem that I'm going to show you, I know that I'm already at the edge of the time that I have, are slightly more complicated problems than MaxCut. So we wanted to see whether we can solve a problem with higher order terms beyond quadratic. And for that, we used this very nice paper by the Los Alamos National Lab team. So they published this paper around finding the ground state of a cubic spin glass, a spin glass with cubic terms. So the cost function is defined in the following way. There are linear terms, there are quadratic terms, and there are cubic terms. In this case, the topology of the model respects the device topology, and the coefficients, these that you can see in the cost function, can be chosen at random between the value plus and -1. So there is actually a pictorial way to understand this model. The colors of the nodes that you see in the graph, whether they are green or red, will tell you whether the linear term is plus or -1. The colors of the edges between the nodes, whether they're green or red, will tell you whether the quadratic terms, these dij, are either 1 or -1. And the color of the circles that encircle 3 different nodes, whether it's green or red, will tell you whether the cubic coefficient is plus or -1. And of course, you can randomly generate different choices of these, and each such choice, random choice, is a specific instance of this model. And for each instance of the model, you want to find the ground state of this classical spin glass. So before I'll show you the results that we got, let me show you the results that the Los Alamos people showed in their paper. Remember, now we want to find the ground state energy. So being to the left is better, it's lower energy. So here you can see several things. So first of all, at the very, very edge, the left edge, you can see both a classical method, simulated annealing, this is this pink one, and quantum annealers. This is data taken from D-Wave, 2 different devices, D-Wave devices. On the very right of this plot, this very light blue is random sampling. And all these colors that you can see near these random samplings, these are different QAOA that the Los Alamos people ran on different quantum devices. In this case, you can see that the QAOA is a bit different from the random sampling, mainly because these models respect the device topology, so they are a bit easier. But the one thing that is extremely clear is that this is not even comparable to what you can get from annealers or classical solvers or the optimal solution in this case. So when we take exactly the same models, and the Los Alamos people were very nice and generous to share the specific instances and parameters that they used and to share with us their data, we can see this huge shift towards the right. and we can do it for a variety of instances. And few things that you can see here, and we can focus on the one of the instances that I put in a larger plot here. So first of all, random as before is not very good. In this case, you can see that even the local solver struggles much more than in the case of the MaxCut. In this case, if we think about the ground state and then a cascade of excited state, first excited state, second excited state, in this case, the best thing that the local solver found was the 8th excited state. So if you want the 9th state in terms of the energy ladder, we can consistently find the true ground state. And for this specific instance, we actually had data from D-wave execution. And the best solution of the D-wave execution in this case found only the second excited state. So in this specific instance, not the ground state and not the first excited state. And for other instances, for some of them, in both methods found the true solution. And in some cases, we were able to slightly outperform. The next slide is my summary. So with that, I will end. But one thing I want to make very, very clear. We are not claiming that for any problem or that we can outperform annealers in a way that is cannot change. I mean, already after we published our paper, D-Wave themselves found some different embedding and ran these problems on slightly different devices and showed that they can improve a bit. And I'm assuming in the next year or two, or even more, we'll see this back and forth where each part improves a bit the problem. So that's the claim is not that we can outperform annealers completely. But until this work and until not very long ago, the common wisdom was that it doesn't even make sense to compare gate-based quantum computers with quantum annealers on this specific type of optimization problems, because they're just light years away. And that was not a conspiracy. That actually was the data that people collected. What they typically saw is what we note here as random sampling. That was typically the behavior that they saw from quantum computers. And in this case, isn't it true? It doesn't even make sense to compare them. They're completely not comparable. What we showed here is that when you manage the errors correctly using good error suppression, and you also complement that with smart and efficient execution, the results that you can get from the quantum computer can be at least comparable to what you can get from annealers, and in some cases even outperform the results that you can get from annealers. So whether one is better or not eventually depends on what the user consider as the most important parts for them. And I guess that over the next few years, probably both methods are going to improve dramatically, but it definitely makes sense to compare the two. And if you want to compare the two, you need to give the quantum computers a fair chance and making sure that you are using it in the most optimal way as possible. So with that, I'll leave you with the summary. I think I'm already after the time that I was allocated. So I'll take any questions if you have right now. Thank you.
Great, thank you very much, Yuval. That's a nice presentation. Thank you. Round of applause on behalf of all members of the audience. And as Yuval says, we'll now open it up for questions. So if you have a question, either raise your hand using the Zoom software or speak up. It looks like Viv has raised her hand. Over to you, Viv.
Hi. Hopefully I've got everything working and you can hear me. So you're comparing, so that's a variational quantum algorithm you're running here. So you're doing a lot of optimization under the hood, which you didn't talk about apart from to say it's there. So every step of that, therefore, has a quantum cost because you're using the quantum computer to evaluate the cost function. So we know from other examples, like completely different approaches, some of these on annealers too, that you can optimize to the point where essentially you've done so much work in the optimizing that, of course, you've got a very efficient short sequence to get you from initial state to final. But you have to somehow, if you want to do fair comparisons, you have to compare all of that quantum cost in the optimizing process. And that's not so easy to do because now you're a bit apples and oranges. If D-Wave hasn't done anything like that, you know, it's just done its n samples, whatever n is, and you've done your n samples plus all that optimizing,
Yep.
plus all that classical extra stuff, you're still very apples and oranges here, and you're still on something that is, there's still a little bit of an interesting question how much you can scale that.
Yep. So absolutely, what I showed you here is just a measure of performance. But as you said, there are many other measures like cost, like time to solution. So in the paper, we do give details regarding cost in terms of dollar cost, but also in terms of wall clock. What does it mean to solve a problem from the second that you just press send and until you get the solution? So all these measures are extremely interesting and important. You can also compare the total number of samples that you have across the full optimization, compare, for example, for annealers that also probably use some number of samples. So these are definitely measures that we give them some place in the paper. For now, time and reducing the number of samples was not our main goal, but we definitely show that, for example, for these type of problems, typically the wall clock is about 6 minutes. Now, whether it's a lot or not, I think that really depends. This is truly from the very abstract definition. So that includes, for example, if you think about annealers, just finding the right embedding and so on. So eventually it's for the user to decide what is more important for them. Is that the wall clock of the full procedure, including encoding the problem? Do they care about the sample time? Do they care about the actual dollar cost? Do they maybe just care about performance? Maybe they don't care to pay 10 times more as long as someone can promise that they can get the best solution. So I agree, it's very hard to compare. And when we think about utility, I don't think there is just one definition of what is better than the other. But absolutely, when we compare things, its performance, its time to solution, its cost, its number of samples, all these measures are eventually important, and users can eventually decide which combination is the one that is most appealing to them. And again, I'm welcome to see these details in the appendix of our paper. We give a lot of information regarding cost and total number of samples and wall clock of these operations.
Yes. By the way, what happens if you do the same post-processing on the D-Wave output samples as you do on the IBM output samples?
So we don't have the data, so we just have the cost values that they found. In order to do that, we need to have the actual samples that they sampled, and we just don't have access to that data. But D-Wave themselves are welcome, of course, to try and do that.
Okay, thank you.
Can I now go to Haider Salman, who has his hand raised?
Hello.
Hello.
Yeah, thank you for the talk. I just have a question regarding the error suppression pipeline that you mentioned briefly, and the post-processing aspect that you do at the end. I mean, it seems there are sort of two separate aspects to the whole thing. And looking at the paper on the archive, I seem to recall that when you did the post-processing, the distributions shifted already quite significantly. And it's just difficult for me to get a sense of how important the error suppression pipeline is to the whole process. So, I mean, if you were to present results where one element is turned on and the other element is turned off, so we can actually gauge the relative importance of the different error suppression, I mean, what would that be?
Yep. So you can see it here. So this data has no post-processing whatsoever. There is also no optimization here. I think maybe it was kind of lost when I mentioned that. So in this case, we're just running the same circuit that was pre-optimized with the default method and with our error suppression. There is no post-processing here whatsoever. This is truly the result that you are getting from the quantum computer. And
so this doesn't have the greedy spin.
No. Exactly. No post-processing. Yeah, so I think I wrote there, execution only, no post-processing applied. And this is truly to show what is the effect of only the error suppression. Now, in this case, we can pretty much push it all the way to the edge, to the solution. As I said, as we go to bigger and bigger problems at the scale of 130, 140, it's almost impossible because even 3 or 4 random uncorrelated bit flip will already take you quite far away. So it's quite essential to recover the true solution. But the overall shift is definitely there, and without it, we just pretty much see random distribution.
I see. So okay. So the error suppression pipeline is integral.
Yes.
For this problem. Yeah. Okay.
Absolutely. Absolutely.
And the details are contained in the other paper that you mentioned.
Yes, absolutely. So the error suppression pipeline is independent of this optimization. I would say this is our flagship. We offer that to people not just on IBM. We're not an IBM shop. You can use it on any quantum computer. In particular, on IBM, it's very easy because it's embedded in their system already. But it will be embedded on other quantum computer vendors soon. So we always say this is a must. This is not a choice. We need to make sure that when we run Circuit, it is run in the best way, given the device limitations. We're not doing magics. Of course, we're always bounded by some measure of the device, but at least you want to make sure that you juice whatever you can from the quality of the device. And then on top of that, you can implement any sophistication at the level of algorithmic design or post-processing or anything that you can do to get even better results.
Okay, thank you.
Kathy, I see that you've turned your camera on. Does that suggest you have a question?
Yeah, can you hear me? I can't seem to get the raise hand button to work, but
go ahead.
First, thanks for the very nice talk. And I suppose some people have been following the archive conversation we've been having, and it's really just I think a heads up. I mean, this is very nice work as a physics benchmarking paper, but there's like 40, 30 years of literature on classical benchmarking and especially commercial benchmarking. And there are rules and standards that have been set out for how to measure runtime and how to report your results. And the purpose of those rules is really to make sure that the manufacturers don't try to game the system and report results that are over optimistic in the sense that they don't actually reflect any user experience. The user could not replicate those results. And you know, this work you're doing here is missing the mark in some of those standards and some of those expectations. And so and that's fine as a physics paper, you know, it's fine, but D-Wave has always been compared against classical solvers, and there are certainly going to be readers who are looking at this paper from the point of view of classical, you know, commercial computational benchmarking, and it's going to be seen as trying to game the system. I'll just tell you that for free based upon my 10 years of experience. So you know, you might want to consider clarifying your intentions here and the claims that you're trying to make that, you know, as you just said, aren't intended to be larger claims. There's an assumption that whatever you say about performance could be absolutely replicated by the user in everyday use. And, you know, this requires optimization, and you're not accounting for the optimization time and all of those other things we pointed out. So it's really just you know, be aware that there's a community out there that is going to misunderstand and misread what you're trying to do.
First, I agree that we are happy to add more measures. I will say that if you actually read carefully the paper, I think all these statements appear there. One thing that I want to say, while this is an academic paper, these tools are available to use today for users. So you can press a button and just do that. And we give the wall clock time. So we tell you, you'll see exactly the same results. It will take you 6 minutes. Now, you can say it's a lot or not a lot, or I don't care about wall clock. I want to understand maybe the time post solution given some other metric, which is very fair. But this is not an academic investigation in the sense that we are doing it behind the curtain and people cannot use it. People can define their own problems, not designed by us, can currently, for now, only on IBM devices, but soon on other quantum computers, can just use it, measure the time, see the quality of solution. So in some sense, I want people to try it. We already have some users that gave us some feedback, and some of them are a success. Some of them we had to tweak some things in order to make it work. So that's how I think overall we'll improve our solver. Regarding specific measures for better and better comparison with classical solvers, I'll admit that when we started this work, that was not something that we had in mind. We didn't even think that we'll be at the point that our results will be comparable. So we mainly focused on performance. But as we move forward, we are happy to add more and more measures to make the comparison more sensible. But again, this is not an academic paper. This is a tool that is available for users. You can go and use it.
Any final questions for Yuval? If not, let's thank Yuval again. Thank you very much, Yuval. Interesting presentation. I certainly learned lots. I learned that benchmarking is a minefield, which I have to keep reminding myself.
OMG.
And all that remains is for me to wish everyone a good summer break. And the INQA seminars will start again in September. Thanks, everyone. Bye-bye.